In calculus, we often find the area under a curve, but what happens when we spin that area around an axis? By rotating a 2D region around the y-axis, we create a three-dimensional solid. This process is essential in engineering and manufacturing to calculate the volume of objects like vases, pistons, and bowls. Today, we will master the disk method specifically for vertical rotations. While many students start with rotations around the x-axis, rotating around the y-axis requires a shift in perspective. Instead of thinking about height as a function of x, we must consider the radius as a function of y. Understanding this distinction is the key to solving complex volume problems accurately and efficiently. Before we begin, remember that for y-axis rotations, our functions must be in terms of y. If you are given y equals x squared, you must rearrange it to x equals the square root of y. This horizontal distance from the y-axis to the curve represents the radius of our circular slices. The disk method relies on the simplest 2D shape, the circle. Since we are rotating a region, every cross-section of the resulting solid is a circle. If we can find the area of one infinitesimal circle, or disk, we can sum them all up using integration to find the total volume. Imagine a single thin slice of our solid. It looks like a coin or a disk. Its radius is the horizontal distance from the y-axis to the function, and its thickness is a tiny change in height, which we call a dy. The volume of this tiny disk is simply the area of the circle times its thickness. To find the total volume, we use the definite integral. We sum up all the tiny disks from the bottom bound, c, to the top bound, d. The formula is volume equals pi times the integral from c to d of the radius squared with respect to y. Note that pi is a constant, so we usually keep it outside the integral. Integration is essentially an infinite sum. As the thickness dy approaches 0, the number of disks becomes infinite, perfectly filling the shape of the solid. This gives us the exact volume rather than just an approximation. Visualizing these horizontal slices is the best way to ensure you are setting up the integral correctly. The most critical step is identifying the radius. For a rotation around the y-axis, the radius is always the x value of the function. Because we are integrating with respect to y, this x value must be expressed as a function of y. Always draw a horizontal line from the axis to the curve to visualize this radius. Unlike x-axis rotations where we look left to right, for y-axis rotations, we look bottom to top. Your limits of integration, c and d, are the y-coordinates where the solid starts and ends. Using x-coordinates here is a common mistake that will lead to the wrong answer. Let's work through an example. Suppose we have the curve y equals x squared, and we want to rotate the area bounded by this curve and the y-axis from y equals 0 to y equals 4. Our first task is to convert the function so x is isolated. By taking the square root of both sides, we get x equals the square root of y. Our radius is therefore the square root of y. When we plug this into our formula, we square the radius. The square root of y, squared, simply becomes y. This makes our integral much easier to solve. Now we integrate y with respect to y, which gives us y squared over 2. Evaluating this from 0 to 4, we plug in 4 to get 16 over 2, which is 8. Subtracting the lower bound of 0 leaves us with 8. Don't forget the pi we kept outside. The final volume is 8 pi cubic units. For our second example, let's rotate the line x equals 2y around the y-axis from y equals 0 to y equals 3. This rotation creates a cone. Since the equation is already solved for x, we can move straight to setting up our integral. Squaring our radius, 2y, gives us 4y squared. We integrate for y squared to get 4y cubed over 3. Plugging in our upper bound of 3, we get 3 cubed, which is 27. 27 divided by 3 is 9, and 9 times 4 is 36. Our final volume is 36 pi. Notice how the disk method confirms the geometric formula for a cone. What if we don't rotate around the y-axis itself, but a vertical line like x equals -1? The disk method still works, but the radius changes. The radius is now the distance from our line of rotation to the curve. In this case, we add 1 to our function value to account for the shift. To find the radius for any vertical rotation, always use right minus left. If the curve is to the right of the axis, the radius is curve minus axis. If the axis is to the right of the curve, the radius is axis minus curve. This ensures your radius is always a positive distance before squaring. Sometimes the region we rotate doesn't touch the y-axis, leaving a hole in the center of our solid. This is called the washer method. It is just the disk method applied twice. We find the volume of the outer solid and subtract the volume of the empty inner space. The logic of horizontal radii remains exactly the same. If your region is bounded by two curves, you must find where they intersect to determine your limits of integration. Set the two functions of y equal to each other and solve for y. These intersection points will serve as your c and d values in the integral formula. Remember the order of operations. You must square the radius function before you find the antiderivative. Integrating the radius and then squaring the result will give you a completely different and incorrect value. Always expand or simplify the squared radius first. To summarize, first, ensure your function is solved for x in terms of y. Second, identify your vertical bounds along the y-axis. Third, square your radius function and multiply by pi. Finally, perform the integration and evaluate at your bounds. Following these steps systematically will lead you to the correct volume every time. Let's test your knowledge. If we rotate the vertical line x equals 3 around the y-axis from y equals 0 to y equals 2, what is the radius of our disks? Think about the distance from the y-axis to the line. The correct answer is 3. Since the distance from the y-axis to the line x equals 3 is constant, our radius is always 3. This creates a cylinder with a volume of 18 pi. If you got that right, you are ready to tackle more complex rotations. The disk method is a powerful tool for transforming 2D calculus into 3D reality. By focusing on horizontal radii and vertical bounds, you can calculate the volume of almost any symmetric solid. Keep practicing these setups, and soon these rotations will become second nature. Generated by Vision Solve AI.